Recording this. Today we'll start with a topic called modified equation. So very comfortably till now we've been avoiding how to do truncation error analysis for situations where you have more than one variable. For one variable we did a single variable truncation error analysis and we got the result. But for more than one variable we have been avoiding it till now. So today we'll discuss that. Right. So in the modified equation is the actual partial differential equation that is solved by the scheme that you have proposed. So let's say we're talking about the upwind scheme for the 1D wave equation that we have been discussing in the last lecture. So here in the upwind scheme, we write this 1D wave equation as with using the upwinding idea here. And what we do is we expand all the terms about n comma I. So n comma I is the point for which you have written the governing differential equation or the difference equation in this case. So we expand all the terms about this n comma ith term. So one of these is phi n comma I, phi n plus 1 I. So this is expanded like this. Now remember, all the derivatives we are talking about are at the point n comma I. So I just write it for the first phi t. So phi subscript t is del phi by del t. Okay. So that I've written at n comma I, and all the other derivatives also at n comma I, but I'm not explicitly specifying just to save some work. So we have phi t, phi tt, phi ttt, and so on. Similarly, we also have a term phi ni minus 1. So that we'll again expand about n comma I using the Taylor series. In this case, it's only the x direction. So we have only the x derivatives of phi here. So once we have written the Taylor series expansion of all the terms about n comma I, we substitute them into the main equation. So let's call this equation A. So in equation number A, phi on the left, the time derivative phi n plus 1 I minus phi ni. So that simply takes, it's taken care by these two terms. I just moved the phi ni on the left hand side. So we are left with, and we divide by delta t. So we get phi t plus so this is the contribution, this is the expression for phi n plus 1 I minus phi ni upon delta t. And then we have u times velocity times phi ni minus phi ni minus 1 upon delta x. So for that I use equation number 2. I move phi ni on the left hand side, well the other way around. So we get and we divide by delta x as well. So we get a positive term first. Right. So let's recall what we have done here. We started with the 1D wave equation. That is the equation that we want to solve computationally. We propose a discretization. In this case, it is the upwind discretization because we have analyzed it. We have seen that this is conditionally stable under the condition that the covariant number is less than 1. So we propose this discretization, but now we want to write the modified equation for this discrete or discretized equation. So modified equation is always written for a discretized equation. Okay. Now I'll tell you what exactly is contained in the equation and so on. But right now I'm just telling you a recipe for writing the modified equation. So then once you have a discretized equation, you write the Taylor series expansion for all the terms about the central point n comma I. So once you have done that, you substitute these Taylor series expansions into the discretized equation, that is equation number A in this case, and this is what you get. And now you will rearrange the terms. So what we do is, since our equation was of this form, del phi by del t, which is nothing but phi t, so I keep the phi t term here. Then we had u times del phi by del x, which is u times del phi by del x, and this was supposed to be 0, but now we can see it is not 0. So whatever is left, I'll move it to the right hand side. So this becomes equal to, first I'll write the time derivative terms. This phi x is here, minus phi x becomes a positive phi double x, sorry, times delta x, but there's also a u multiplied, so this is u times delta x, then we have a negative. So this is always alternate positive and negative terms. Right, so this equation that we have here, this is called the modified equation. So this is the actual partial differential equation that is being solved by the computer using this scheme. We wanted to solve phi t plus u phi x equal to 0. But because our scheme is approximate, remember, the scheme was proposed as an approximate scheme to approximate the actual equation. So there is an error associated. So the error associated is this. Okay. So now the reason we've written this equation is because this is the actual equation being solved by the computer now. So we'll analyze the behavior of this equation, because the behavior of this equation might be different from the behavior of the actual equation we wanted to solve. So the solution we get is a solution to this equation, not the original one we wanted to solve. So the behavior of the solution is going to mimic the behavior of this equation. So if we can analyze this equation, we'll be able to analyze the solution, because you might see effects in solution which you did not expect. So you might conclude wrongly that there is some problem with the solution I've implemented. That is not the case, because you're solving this equation. So the behavior of the solution is going to show the behavior of this equation. Okay, so this modified equation has actually tremendous amount of information, not just showing the solution behavior. We'll talk a bit later about this, but this equation, if we are able to analyze, this is containing a lot of information. So we have written the modified equation. The next step, since we want to do the truncation error, because the discussion today started with this idea that the truncation error analysis that we have been doing till now is quite simplistic. So we want to do a better job at doing truncation error analysis. So we are writing the modified equation. So now what we'll do is we'll see how we can do a better truncation error analysis using this modified equation. Now what I see is that my error, which is on the right hand side, contains terms which have delta t and delta x as the largest order error terms in t and x. So I could conclude, or I would conclude, Well, actually, I'm sorry. I want to correct myself. This is not the modified equation. Modified equation is when we eliminate all the time derivative terms. So let me go back. I apologize for this mistake. So modified equation is obtained when we eliminate all the time derivatives in the error terms. On the right hand side, we have time derivatives which look like this: phi tt, phi triple t. So these are time derivatives. So once you eliminate these terms using a technique that I'll discuss now, then we get the modified equation. So this is not the modified equation. Okay, so let me remove this red box around it. So now using this intermediate equation that we have, if we concluded that the scheme is order delta t delta x using the above equation or above expression, so we could be wrong. And that is what we have been doing till now. That's what we did, right? So we wrote the error terms on the right hand side, and we saw that the leading error terms are order delta t and delta x. So this scheme is order delta t comma delta x. Now in this case it is correct. This scheme actually is order delta t delta x. But this idea does not work correctly in all situations. I'll give you an example to work at home. So we could be wrong. So could is the word here. It's not that we'll always be wrong, but we could be wrong here. So the only way we can write or we can figure out with confidence what the error of the scheme is if we write the modified equation. So modified equation is when you eliminate all the time derivatives in the error term on the right hand side. So let's do that. Okay, so in this equation that we have, we'll eliminate all the time derivatives now. So the first thing we'll eliminate is phi t t. So the second partial derivative with respect to time. Now how can I get rid of phi t t? So I can, so let's call this b. So if I differentiate b with respect to time, I'll get a phi tt from this expression, right? And then I can multiply that by the correct coefficient and then add the equation, then get rid of phi tt. So that's how we proceed. Okay, because this equation number b is the actual equation solved by the computer. So I can use this as many times as I want because this is the equation being solved. So derivative of this equation will also be satisfied. So I can just take derivative. So what I do is I'll write phi tt from b by taking del of this equation b by del t. So this gives me a phi tt from the term here. And this phi x term now becomes phi xt. So I'm then everything else will also get modified. So in the first bracket, my phi double t now becomes phi triple t. And the second phi triple t now becomes the fourth derivative with respect to time. Similarly, for the x derivatives on the error, I get mixed derivatives now. So phi xxt, and then I get phi xxxt, and so on. So the aim was to get rid of. So what I can do is now I can take equation number B, and in B, or what I can do is I can multiply this expression that we have above by delta t by 2 factorial. Or basically I just substitute this into B. So this expression for phi tt, which is written in terms of higher order derivatives of t, because all these derivatives of t now become one order higher. Because when you differentiate that with respect to t, they become one order higher. And all these pure derivatives of x now becomes mixed derivatives, and so does this pure derivative of x. Okay, so we substitute this phi tt into b. So on the left hand side we still have the same thing. On the right hand side, the first phi tt times delta t by 2 factorial. What am I doing? Yeah. So this becomes, so the first one we get is phi xt. So this phi xt is going to be clubbed with the mixed derivative. So first I write the pure derivatives with respect to t. So basically I will start with the phi triple t now. So this becomes, now the earlier coefficient of phi triple t was delta t squared by 3 factorial. But I have added another coefficient this time. So when you substitute phi tt here, so what you do is you generate phi triple t coefficient, which is delta t by 2 factorial with a negative sign, but now you also have negative delta t by 2 factorial here. So this becomes a positive, so I'll write the coefficient here, delta t squared by 2 factorial times 2 factorial, so that is 4. Okay. Now I don't want to write all the terms, this becomes very tedious. I just want to give you a couple of terms. So then you have all other pure derivatives with respect to time. So what we have seen is phi tt is gone. In the error now we have higher order pure derivatives of time now. But we also generated some mixed derivatives. So one mixed derivative we generated was phi xt, whose coefficient is minus u, but we also have a minus delta t by 2 factorial. So that becomes, because we substituted that here, so a minus minus becomes plus, so we have a plus u delta t by 2 factorial. So that's the only coefficient of phi xt that we have here, right? And then we'll have phi xxt. I'm not writing the coefficient, and so on, because you generated a phi xxt like this, and phi xxt, and so on. So these are the mixed derivative terms. And since this is because of substitution, but we already have this original pure derivatives of x also. So this we'll just include as it is, which is phi x times something plus phi x times something and so on. It's pure algebra, nothing else. Okay. So if you have the patience and the time, you can do it. And you continue. This is just one step. You continue with other steps. Now, is this clear to everyone what we have done here? I'll show you other steps as well. I'll show you more steps in a while. In fact, I'll show you how to do a better. In fact, you can write a program to do a modified equation analysis. What we did was we got rid of phi double t. Okay. And that's what we wanted. But we want to get rid of all time derivatives. That's the whole aim. Now this work is infinite because if you get rid of phi tt, you generate phi triple t. So what we do is we have to decide when to stop. So I'll say that I don't want terms which have, or I will only live with terms which have a third order derivative or higher. So I have to get rid of all the terms which have less than third order derivative. So right now I still have this term called phi xt. I have phi x xt. So I have to get rid of these terms as well. So we'll see how we do that. So let's make a table here. So basically what I'll do is I'll write all the all the terms I can have. So I can have, in my equation I'll have a phi t term, a phi x term, then I'll have a phi tt term, then a phi tx term, then phi xx term, then let's come to third order derivatives, which is phi triple t, then I can have phi double tx, then phi txx, and then phi xxx, and then I will have higher order, but I'm not worried. I will stop at, let's say, third derivatives. So now my equation number b, which I had, which was this one, the coefficient of phi t was 1 and phi x was u. So I write the coefficients below this. The coefficient of phi t was 1, phi x was u. And then now what we'll do is, since we are writing coefficients, we'll move all the terms to left hand side and then make it equal to 0. Okay, so the equation is written in such a way so that we have all the terms on left hand side and right hand side is 0. So the sign will change again slightly. So here we have the coefficient of phi tt as delta t by 2 factorial with a negative sign. Since I move it to the left hand side, it becomes delta t by 2 factorial with a positive sign. So I get delta t by 2. What about phi tx? That was not there in the original equation, so that the coefficient was 0. Phi xx was there. If you look at it, phi xx had a coefficient of u delta x by 2. So this becomes now minus u delta x by 2. Now I'll write all the coefficients rather than moving up and down. So this becomes delta t squared by 3 factorial, which was 6. There were no mixed derivatives in the original equation. And then phi xxx had a coefficient of u times delta x squared by 6. And again, we are not worried about fourth order derivatives here. Right, so what you did was so this was b. So what you did was you did del b by del t, and you multiply that by a minus delta t by 2. That's what we did. I mean, we did it in a different way. So when you do del b by del t and you multiply that by a minus delta by 2, let's write the coefficients now. Now it's not that difficult because when you do del b by del t, this phi t becomes phi tt. So the coefficient goes into phi tt. The coefficient of phi t was 1 in equation number b, and you have multiplied that by delta t by 2. So the coefficient of delta t by 2 becomes, the coefficient of phi tt becomes minus delta t by 2. Next was phi x in equation number b. So when you take a derivative with respect to t, you generate phi xt or phi tx. The order of derivative does not matter. So phi tx term is generated, and the coefficient of phi x was u, and I've multiplied that by minus delta t by 2. So this becomes minus u delta t by 2. The third one was phi double t. So phi double t, you take a derivative, you generate phi triple t term. So the coefficient of phi double t was delta t by 2. You multiplied that by minus delta t by 2. So that becomes minus delta t squared by 4. Now phi double x has no coefficient because you took a derivative of equation number b with respect to time. So that equation will not have any pure x derivative. So this will be 0. And then what about phi t tx? That will also be 0 because you did not have a phi tx term in your original equation. So you cannot have a phi t tx by taking derivative of b with respect to time. So this is 0. Phi txx will be there. So phi xx was there. This one. If you take a derivative of this with respect to time, you get a phi txx or phi xxt, whatever. So the coefficient of that is going to be minus u delta x by 2 times minus delta t by 2. It becomes a plus u delta t delta x by 4. Clear? So now I know with confidence that if I add these two, then the coefficient of utt will become 0. Okay, good. But there are more steps associated with this. The next step is I have to get rid of this term, which is phi tx that I have generated, this one. So for that, what I do is I take the derivative of equation number b with respect to x this time. So this term will become phi tx, and I follow the same strategy to eliminate the coefficient of phi tx. See, we will move from left to right. So we will try to remove all the terms which have a time derivative in it. So I have removed this one. So this is done. So now I have to remove phi tx, phi ttt, phi ttx, phi txx, and so, and that's the these are the terms I'll remove. So I've done this one. Good. So now we move to the next one. So I'll just do one more step and then I'll put a dot and summarize. But I expect you to go home and try to do it completely. So del b by del x, and then since we want to get rid of this term which has a coefficient till now, we take the total sum. So total sum till now is minus u delta t by 2. So I want a plus u delta t by 2 here. Right? That's the only way I can cancel it. So how do I get that? I do a del b by del x. So this term has a coefficient of 1 only till now. So I multiply that by u delta t by 2 and add. And in this process, when we do del b by del x, I generate a phi xx term here. Okay, so this term phi xx will have a coefficient u square delta t by 2. Then when I multiply this by, when I take a derivative, so I can generate a phi ttx, which is here, and the coefficient of this is going to be u delta t square by 4. Then when I take a derivative of this with respect to x, I generate a phi t x term, which is here, which is u delta t squared by, no, this is, sorry, del b by del x. So we just generated, so we have a phi t, no, a phi t x, so the coefficient of this was 0 anyways, right? So if you take a derivative, you don't get anything. So this phi t x, so I'll not write anything there. And then we had a phi xx, so that becomes a phi xxx, so I generate something here, which is minus right, and so on. I think that's pretty much it here. So now we are we have ensured that the coefficient of phi tx is also becomes 0. Now the next exercise is to make phi t dt. So for that, what we'll do is del 2 b by del t2. Basically, we always use this term to eliminate. So we have to make this phi t into whatever we want. So this is del 2 b by del t2, and then you multiply that by delta t squared by 12, because remember till now the coefficient of phi triple t is the sum of these two. So whatever that is, the opposite sign of that has to be multiplied. Okay, so I'll not do this, you can do it yourself. And then what you see is that in the end you will have a phi t term, you will have a phi x term, phi tt is gone, phi tx is gone, then you will have a phi xx term, and then we'll have a phi xxx term, and then we may have higher order terms which will contain t, but that's okay. So now what I do is I write the expression for you, and then we will talk about the expression or discuss it. So now again I move all the terms to the right hand side except the phi t and u times phi x terms, so that I see the error now. So this is called the modified equation, and this equation has tremendous amount of information and importance. So important that every exam will have a question on this with a significant 10-mark question. Then I have given you how important this is for you for the exam. But in general, this equation is very important. So everybody must know how to do the modified equation analysis. So in the next class, which is going to be on tomorrow, right? So tomorrow is Monday's schedule. So Monday we have a class at 1. So tomorrow we'll have a class at 1 p.m. So tomorrow I'll show you what is the importance of this equation and how much, what sort of information you can extract from this. So we can extract truncation error analysis, that we'll show you. we can extract stability information from this. Remember that von Neumann analysis we did? That is also available here. And in addition to that, we can also extract the nature of the error. So which we'll discuss in the lectures to come. Errors can be either dispersive or dissipative. So we'll discuss that nature of the error can also from this equation. So this information has lots of information. This equation has lots of information, and that is the reason it's worth knowing about this. So we'll stop here now, and I'll see you tomorrow.
Sir, in the term table